Sources emphasize how important it is. So how does math help us understand the physical world?
Mathematics is absolutely crucial to physics. It's the framework for building knowledge and describing the world precisely. It lets us create models of natural phenomena and connect those models to experiments. Mathematical equations are a powerful way to connect symbols representing physical quantities through relationships like addition, multiplication, and division. They condense complex relationships into simple statements. In physics, we give these symbols specific meanings like m for mass and a for acceleration, and then math gives us the rules to connect them.
So math is like a universal language for physics.
Exactly. And a key concept is semantic density, which is the amount of meaning packed into a single item like an equation. Mathematics increases the semantic density of physics by letting us create precise relationships between those defined symbols. An equation with many interconnected symbols, each with physical meaning, has high semantic density because it holds a lot of information as a compact form. Like Einstein's famous equation E equals mc squared. It's short, but expresses a profound connection between energy mass and the speed of light.
So a simple equation can hold a huge amount of information. What about connecting those abstract mathematical relationships back to the real world? The sources mention semantic gravity.
Semantic gravity is about how much the meanings of those symbols and their relationships depend on the real-world context. General equations like F equals ma have weak semantic gravity because they apply broadly across many situations. They're not tied to a specific case. But when we put specific numbers into those equations to describe a real event, which is called quantification, the semantic gravity becomes stronger. For example, when we calculate the acceleration of a space shuttle using F equals ma and plug in the actual thrust force and mass of the shuttle, we're connecting the abstract theory to a concrete observation.
So quantification grounds the theory in real measurements, and the sources also mention derivation as a key role of math and physics.
Right, derivation is about manipulating existing equations, using mathematical rules to create new equations. This lets us make explicit relationships that were hidden before. For instance, starting with F equals ma and using the definition of acceleration and momentum, we can derive another equation for force as the time rate of change of momentum. This process of derivation increases the semantic density of physics by expanding the network of concepts and relationships, giving us deeper insights. Ultimately, mathematics gives physics two powers: theoretical development through derivation and connecting theory to data through quantification. This back and forth between abstract and concrete is essential for understanding the universe while staying grounded in observations.